Hello everyone, welcome to Introduction to Electric Vehicles Charging Station Systems. I am Dr. Shailendra Kumar, Assistant Professor in the Department of Electrical Engineering, IIT Bhilai. Today we will see the operation and control of EV charging systems, as these two parameters are is very essential for any EV charging systems. We need to follow the modes of operation of a charging system as well as the control, either it is onboard or offboard charging systems. The control is very essential. Control has to be integrated with these EV charging stations. So, under this we will see introduction over operation and control. Then very important, we will see vehicle to grid and grid to vehicle operations, as these bidirectional charging systems are very famous. Instead of having only grid to vehicles, under grid to vehicle we are drawing power from the grid. However, whenever there is huge load demand or peak load demand, under that conditions our electric vehicle should operate in vehicle to grid mode, so that they can support the electricity grid during peak load demand. We will also see future trends and challenges. We will see what are the future trends and what are the challenges for these vehicle to grid operations and new technologies. Characteristics of unidirectional and bidirectional power flow operations. Bidirectional charger operations with V2G and G2V, and then other type of bidirectional charging system, and finally we will see the summary. So, here operation and control techniques which are involved in the EV charging system. This operation and control are critical for any charging station, so that it can ensure the reliable operation, efficient, it should operate in safe zone, so that we can, under these conditions, we can supply power to electric vehicles. These stations must manage the power flow between different quantities, different entities, optimize energy uses and maintain the stability of local grid by maintaining grid parameters, while catering to the need of multiple EVs. So, it is not like that only one EV is connected at the charging stations. We may have multiple EVs which are connected in a single charging station. So, among these EVs, this power flow must be managed, as well as the stability of the grid must be maintained. Control technique focus on managing energy flow between EV and the charging infrastructure, while integrating these EV with the grid. So, these control, as I told you, controls are very essential part for managing energy flow from the source to the vehicle, and when we are operating these vehicle and V2G mode, then we need to control the charging discharging and of the batteries. Effective energy management and control techniques are crucial for optimizing the performance, efficiency as well as life span of electric vehicle systems. Lifespan of the batteries is very important, as one battery may last longer for 4 to 5 years, but if it is going for deep discharge and overcharged, the lifespan of the battery can be decreased. So, we have to apply proper BMS, proper energy management control in the charging station, so that we can control the battery parameters also. Therefore, we need this battery management system. So, BMS is responsible to monitoring and managing the battery pack, health of the battery pack, I would say, ensuring safe operation, longevity and optimal performance. Now, this SOC estimation is also one of the important aspect of a charging station, which should be accurately determined. I mean, these SOC estimation, people are using various technique for state of charge estimation. There are various technique like Coulomb counting method. People are also using some adaptive technique, Kalman filtering based technique people are using for SOC estimations, which determines the remaining battery charge to prevent from overcharge or deep discharge. As we have discussed, thermal management, which controls the battery temperature to prevent from overheating and improves the efficiency of the battery. Cell balancing, which ensures all battery cells are charged and discharged evenly. There is no such situations where some of the cells are overcharged and some of the cells are having less charge. So, uneven distribution of charges must not be there, which extend this battery life if the charges are evenly distributed in the cells. So, first we will go through the energy management scheme. The function of energy management is optimization energy distribution between the vehicles, powertrain, auxiliary systems and regenerative braking. Sometimes when we have these onboard charger in the vehicles, so regeneration may take place from the motor drives part. When we are applying the brake, the energy is restored in the inertia in the form of kinetic energy. This kinetic energy can be utilized to charge the battery, which is available at the along with the electric vehicles. So, these renewable energy braking is also there. So, EMS is playing important role whenever we are going to have different type of energies and different type of resources in the system. So, we may have rule based strategies. Predefined rule governs the energy distribution based on driving conditions. We are driving in urban area or we are driving these vehicles in the highway. Optimization based strategies, control like MPC, model predictive control, which may optimize energy uses dynamically based on real time data. Now, we have vehicle to grid operation. So, the main duty of vehicle to grid operation, whenever there is peak load demand, we need to inject energy or we need to support the grid by discharging our electric vehicles through these DC-DC and DC to AC stages. Under this scheme, we need to regulate battery discharging operation. Battery should not be deeply discharged, which could finally may affect the battery life, and we have to prevent this battery when we are operating under vehicle to grid mode from overcharged and over discharge. Track the SOC of the battery to ensure proper charging and discharging operations, and provide appropriate value of SOC and DOD to the user. So, using these Coulomb counting based conventional technique or some advanced SOC estimation based technique like Kalman filtering, it can be integrated, and they may give the exact estimation of SOC and DOD of the battery, and they can provide the information to vehicle to grid control. And this finally, the control of EV battery SOC is, that is why this control of EV battery SOC is essential. What are the operating methods? We may operate in vehicle to grid, where power flow from EV to the distribution grid. We may operate these electric vehicle in vehicle to home or vehicle to building mode. If you have aggregator, multiple electric vehicles are combined at the aggregator, and these aggregator can supply energy to the building or to the distribution grid. Because integrating only one EV to the grid, it may not be very efficient. To integrate all the vehicle, we require aggregators, so that overall efficiency of the system, of the charging system, can be improved. We have vehicle to load mode, power flow from electric vehicle to the loads. Another important technology, that is vehicle to vehicle mode. Suppose I have one vehicle which is not required to drive within 4 to 6 hours, and another person has the vehicle and the battery of that vehicle is empty. So, this technology is very essential in this manner. I can supply, I can allow my vehicle to discharge, and from my EV battery the power can be transferred to the other EV batteries. So, power flow from one EV to another EV, that can also be included in the operation of this, or operation and control of EV charging systems. What are the future trend and challenges? This bidirectional charging is the future trend, where EVs as energy storage for the grid deployment. EV not only consume energy, but also provide energy back to the grid during peak hours or emergencies. What are the impacts? Enhances the grid stability. Whenever we have vehicle to grid operation, voltage and frequency can be maintained, and we can integrate renewable energy resources with the grid and provide financial incentives to the EV owners. Increased renewable energy integration in EV charging infrastructure can also be one of the future trend, and people also integrating these renewable energy resources with the grid nowadays. So, need for advanced grid management, smart charging technologies, and robust infrastructure to support EV growth. However, the challenges: high penetration of EV can lead to grid overload, voltage instability, and increased peak demand. Diverse charging standard and protocol across region, and manufacturer complicate global EV adoption. Insufficient charging infrastructure, especially in rural areas and underdeveloped areas, hinders widespread EV adoption. High upfront cost of fast chargers, grid upgrades, and renewable energy integration can be a barrier for adoption of electric vehicles. So, now we have two main charging systems that are known as unidirectional and bidirectional. So, if we see unidirectional, where we are going to supply power from grid to vehicle only. So, if we see the first feature, power flow, the charging rate of EV control with the unidirectional power flow, which is based on energy scheduling of grid to vehicle, and unidirectional power converters are required in that case. However, G2V and V2G mode enable bidirectional power flow to achieve a range of grid support and services. Both the way we can inject energy to the grid and we can draw energy from the grid. So, this bidirectional charging systems are very essential, and this type of technology is very famous. Type of switches, as we know, we can use various converters. So, mostly in case of unidirectional chargers, people are using dart bridge rectifier followed by one PFC converter, it may be boost converter and DC-DC stage. So, using this control, people are doing PFC, power factor improvement they are doing, and they are using these two stages. However, in case of bidirectional charging system, we require control switching. So, for AC to DC stage, IGBT based inverter, or for low power applications we can utilize MOSFETs, but for medium power applications or for high power applications we have to utilize these IGBT and high power gate thyristors. So, other features, services, other features, services, ancillary services, load leveling, load profile management and frequency regulation under unidirectional charging. However, in case of bidirectional charging, voltage and frequency regulation can be done, backup power support during peak time, active and reactive power support can also be done, and which may help to integrate these renewable energy sources with the grid during bidirectional charging systems. Control system, a simple and easy control system, active power of charging system and energy pricing techniques used to manage basic control. However, a complex control is required in case of bidirectional power flow. Additional control devices and driver circuits are required, which measures an accurate, which require an accurate communication systems, controllers and some sensors are required in that gate. Safety, isolated and non-isolated converter can be utilized for unidirectional charging. In case of bidirectional charging, isolated and non-isolated converter can also be utilized, and which may include high safety measures and anti-islanding protection also, because sometimes grid may disappears, sometimes grid may appears. So, in that case protection as anti-islanding protection must be there. Advantages: simple power flow control, minimize operational cost, as from AC to DC conversion we are using only diodes. So, these devices are less costly as compared to IGBT and this bidirectional converters. Advantages of bidirectional charging system: improves voltage profile, power quality, active reactive power support, load leveling, load voltage, load and frequency regulations, and it also enables renewable energy integration with the grid. Limitation: unidirectional charging system has limited services and it requires a power connection, no extra degradation in battery can be observed in case of unidirectional charging. However, in case of bidirectional charging, there is power flow in two ways. So, we require bidirectional communication or bidirectional control. Complexity is high, as well as when we are operating in vehicle to grid mode, we have to discharge the battery. So, it may be possible there may be a degradation, fast degradation from the battery side. Now, we will see the applications of bidirectional charging system. We will select one topology and we shall try to see what would be the basic control and what are the simulated results, and then how it can be verified in real time scenario. So, we have bidirectional charging operation with V2G and G2V. Battery charges mainly consist of two stages. We can see in the figure where we have grid 3-phase AC supply and it can be converted into AC to DC. So, rectifier plus PFC stage are there, and then we have DC-DC converter stage which may control the battery charging and discharging current. So, there are few highlights of the bidirectional charging operation. EV batteries are charged through the grid in grid to vehicle mode. However, EV batteries are used to feed power to the grid in vehicle to grid mode. The control of the bidirectional converter is used for DC link voltage control. So, regulation of DC bus voltage is very essential, otherwise there is no proper energy transfer between AC bus and DC bus. Another important feature in this particular topology, the same converter which is utilized for DC to AC and AC to DC conversion, it is giving ancillary services like mitigation of harmonics, compensation of reactive power, and it is very feasible for commercial utilities. The effective of the presented systems, or we can say multifunctional charging systems, where apart from vehicle to grid, grid to vehicle operation, we are providing reactive power compensation, harmonic mitigation, power quality improvement using advanced adaptive control. They can be validated. I mean, here we have validated these control, and some of the results we are showing in form of simulation and real time test result. So, this is the bidirectional charging system, where at the DC bus we have connected various bidirectional converters. You can find out two switches and one inductor. So, here we have used IGBTs to develop this bidirectional DC-DC converter. So, again if we go from left to right, we have electric vehicles where a battery is inside the vehicle, and these vehicles are connected at the DC bus via bidirectional converter, and these bidirectional converter allows current from DC bus to EV battery, as well as if EV battery is available to discharge, then it can be also discharged from same port. So, here we have connected 3 EV batteries. However, we may connect number of EVs battery at the DC bus depending on the capability of the system. After this DC bus, we have DC bus capacitor. Across this capacitor we need to maintain the bus voltage, so that the energy transfer must be proper at the vehicles as well as toward the AC side. And after this DC bus, there is one 3-leg voltage source converter which has 6 switches. We assume, I mean, we have taken a 3-phase system. So, 3-leg voltage source converter we have to utilize, and then we have interfacing inductor, and then some filtering units are there in form of filter inductor and RC, and point of common coupling is there where we can connect some onboard chargers, some residential loads if required, and then we can connect this system with the 3-phase grid. So, here the two waveforms we have shown in form of grid voltage and in form of grid current. So, rightmost waveform where it is written Pg is positive, which means the power is drawn from the grid and the system is operating in grid to vehicle mode. Here we can see both grid voltage and grid current are in same phase. However, if we see the other diagram, the grid current is out of phase with the grid voltage, and we have considered in such scenario the current direction is reversed, and now the power is injected to the grid from EV batteries or from the onboard charger which is available at the point of common coupling. This type of topology we have published in some good journal like IEEE CSEE Journal of Power and Energy Systems. And we have also developed the multi EV charging spots where we have various electric vehicles and they are rated at different voltages. We have voltage range from 48 to up to 400 volt, or we can say if we are integrating at the 700 DC bus. So, the voltage at the vehicle side can be further increased, like Tesla may have 600 volt or 400 volt. So, that vehicle can also be integrated using DC-DC converter at the DC bus. So, these DC-DC converter units, they may be isolated or non-isolated, and it can be utilized to interface these units with the DC bus. Design of this particular charger. So, we need to design the inductance value which we have selected for bidirectional charging system. Here the battery has been selected, EV battery like 240 volt and 20 ampere hour, and the switching frequency that is playing a major role for selection of this inductance, as it is inversely proportional with the inductance. So, as soon as you are going to increase the switching frequency, the value of inductance or inductor which is utilized for developing this DC-DC converter is reduced. Here we have taken 20 kilohertz as we have used IGBTs. So, the inductance value is selected around 2.5 millihenry, and here we have chosen a 230 volt, remember 230 volt AC grid. However, in practice people are taking 415 volt AC grid, but in laboratory through auto transformer you can vary the grid voltage, you can step down the grid voltage up to some extent and you can integrate your system, right, because in laboratory every time you will not get facilities where the high power system can be developed. Sometimes for verification of concept you have to develop low power prototype. So, here we have selected 230 volt AC grid, and with respect to 230 we have derived the DC bus voltage. So, using this formula 2 root 2 VLL divide by root 3 and into M, we have decided the VDC, and this VDC is inversely proportional to this particular what we can say, when we need to select this VDC, we have to know the V line to line voltage, and accordingly we can select this 400 volt, where M is the modulation index and M will decide the voltage which we have at the output of the converter. So, the VSC is switched at very high switching frequency, and at this frequency we have various harmonics which are generated, and for this purpose, to mitigate high frequency ripple in the voltage, we have connected one RC filter. So, this is the control which we have utilized for this DC to AC or AC to DC conversion unit, where the load currents are sensed, 3 phase load currents we have sensed, and 3 phase voltages are sensed to get unit templates. Unit templates are nothing but they are synchronizing signals. The moment when you want to synchronize your charging station with the grid, you need to maintain certain parameters. If you are able to maintain certain parameters of the at the output of the converter, then only this converter will be synchronized with the grid. So, here we have 3 load currents, and after taking the average, other side we have charge controller which can control the charging and discharging of these EV batteries. We have initiated the reference current, and these reference currents are compared with the sensed grid currents and given to the hysteresis controller, which may give the switching signals for voltage source converter. So, the theory we have given here, and then we have also given some comparative analysis, because here we have used some advanced control, adaptive advanced control, and we have compared this control with the traditional controls like synchronous reference frame based theory, where we need to use some transformation blocks, right, and we can see the computational burden in these controls as well as the transient speed, controller speeds, what are the sensor requirement, and what are the payback time of these control technique, the system which has been developed with these control technique. Now, other control is bidirectional converter for battery. So, here we have used cascaded based PI control to control the voltage at the DC bus and battery current. So, the difference of sensed voltage and reference voltage is given to the PI controller, and the output of first PI controller is considered as the reference for battery current. I mean, it is considered as a reference battery current, and then it is compared with the sensed battery current given to the second PI, and the output of this PI is considered the duty ratio. This is compared with the triangular wave of 10 kilohertz, and then the switching signals are initiated. So, this way we can go to the simulation results. So, first we have performed the G to V, and the other figure it is showing V to G. So, the at certain time, like in first figure from at 1.75 the mode transfer has been taken place. So, the system is switched from grid to vehicle to grid, and the other parameters. So, here from grid to vehicle, the currents and voltages are in same phase. However, after switching to E to G, the power is transferred to the grid from the vehicle batteries. So, both voltages and currents are become out of phase, and vice versa scenario we have observed in other figure. Here we have shown the various powers. where the SOC of the battery is decreased and increased simultaneously for vehicle to grid and grid to vehicles, and respective voltages and current are shown here. This is the dynamic performance of the charging stations, where one of the phase is removed. Suppose there is single phasing or one single phase onboard charger is connected and other phase is removed, or there is no power requirement from the other phase. So, how the currents and voltage of the grid will behave. So, here we need to maintain grid currents sinusoidal, and we can see under load unbalancing the grid currents are balanced, and at the right side, as these chargers are behaving as a non-linear loads. So, the total harmonic distortion of the charger is around 16.84. However, the grid currents TSD is maintained within the IEEE 519, which is 3. Here it is 3.73. It should be less than 5%. And the real time results. So, we have verified this type of topology, this vehicle to grid, grid to vehicle operation in the real time using Opal RT based hardware unit. So, here we have certain results like grid to vehicles, vehicle to grid, and then we can see under steady state condition both grid voltage and grid currents are in opposite phase. However, in other feature we can realize the grid voltage and grid currents are out of phase. So, this way we can realize both the operations, and then test result under load perturbation, and then we have also realized the comparative analysis among these conventional systems, conventional controls, as well as the control which we have used for controlling of charging station. So, here we have summary. Thank you for participating in this today lecture for an operation on and control of EV charging system. We have seen the vehicle to grid, grid to vehicle operations, what is the unidirectional and bidirectional charging, a very wide comparison between the bidirectional and unidirectional charging. So, I hope this session has provided valuable insights and deeper understanding, and we are looking forward to seeing you in our next session. Thank you very much. Here we have few references which can be followed for this topic. Thank you very much.